Greetings and welcome. In this session, we will see the procedure to solve the numerical of a complete two-stage refrigeration system. So we have seen theoretical part of the system, that is a pH diagram and a schematic diagram of the multi-stage, that is complete multi-stage refrigeration system for two compressors. Now that by using that concept we will solve the numerical. So let us first of all see the statement of the numerical. In this statement, what is given? Complete two-stage compression refrigeration system is having capacity of 30 TR, means cooling load is given, used to achieve a minimum temperature of minus 20 degrees Celsius. This is the temperature of evaporator, means this is the exit temperature of evaporator, or entry temperature of compressor 1, means point number 1 minus 20 degrees Celsius for the location on the chart. System uses R22 refrigerant, means type of chart R22 we have to use. When the ambient temperature is of 40 degrees Celsius, this is ambient temperature, means condenser temperature where the heat rejection process is taking place. So condenser exit point saturated liquid, on the saturated liquid line of the pH diagram R22, 40 degrees Celsius temperature we have to use. The refrigerant from the low pressure compressor is intercooled in a flat chamber at 0 degrees Celsius. Now here in some numericals pressure, intermediate pressure is given. In this numerical here intermediate, here where flat chamber, at the flat chamber at which temperature that line is coming and that line is going to the next evaporator. So this is a middle temperature given. So there will be three temperature lines in the pH diagram. Higher temperature condenser temperature, that is a 40 degree Celsius. Lower temperature evaporator temperature, that is a minus 20 degrees Celsius. And middle line, that is intermediate pressure line or flash tank, that line will be at 0 degree Celsius. So in this way here is a difference in this numerical came. In earlier numerical, bar pressure values, intermediate pressure value was given. If you see previous two videos, that is flash gas removal method and intercooling method numerical. Remaining is what's assuming that the refrigerant entering to each compressor is dry and refrigerant leaving the condenser is saturated liquid. Means here compressor entry vapor is a dry saturated and condenser exit liquid, that is a saturated liquid condition. Compression is isentropic. Now we have to calculate here mass flow rate, power and COP of the system. Now we have to first of all see how to plot the pH diagram, how to plot the cycle on pH diagram of R22. So here we can see this is a graphical representation of R22 refrigerant pH diagram. Now here, as per the given data, minus 20 degrees Celsius evaporator temperature. This is a evaporator temperature evaporation process line. Left side, right side. Here you can see minus 20. So on the right side here on a saturated curve vapor line, this is a vapor line and this is a liquid line. So on a vapor line here at a minus 20 degrees Celsius, you locate the point, that is a entry point of the low pressure compressor C1. We located this point number 1. Then condenser side ambient temperature is given 40 degrees Celsius. So at a 40 degrees Celsius means on saturated liquid line 40 degrees Celsius, you locate the point number 5, that is the exit of condenser. Then third temperature, that is flash tank temperature. So that temperature is given here 0 degrees Celsius. So you can take reference of this 0 and you draw the horizontal line through this point. Now you located now 3 points. Point number 1, point number 5 and point number 7. Now remaining points how to obtain, that already we have done in earlier video sessions of numericals. Same methodology used here, means what? From point number 5 you draw a vertical line, as the process is isenthalpic constant enthalpy process in upper envelope in expansion wall. This is low pressure envelope, here expansion process, so 7 to 8. This process will be vertical. So this 7 line from the 7 will cut or meet to this evaporation line. Here will be point number 8. Here this point number 5, which is dropping or vertical coming from this condenser point, will meet to this intermediate temperature line of flash tank. This point you will get intersecting, that is point number 6. So in this way we found these points. Now about the right side, here point number 1, through this you draw the line parallel to the isentropic lines which are here. So taking reference of isentropic line, you draw this curved line, and this line will meet to this intermediate flash tank line, and here intersection point you will get, that is point number 2. Also you will find the point number 3, that is a entry point of the next compressor, because as in the statement it is mentioned that condition of vapor passing to the both compressor is a dry. So point number 1 is a dry, point number 3 is a dry saturated vapor. So that is why here you can locate point number 3. Same method of 1, 2 you can apply for this, and you can draw this 3, 4 line parallel to the isentropic lines, and this 3 line from 3 point, this line will meet to this condenser line at point number 4. So this will be exit of compressor, point number 4. So in this way all the points we located on the pH diagram. After that, through all these points, draw the vertical lines, drop the vertical lines on the enthalpy scale and get the values of enthalpies. So here point number 1 you will find enthalpy H1, point number 2 H2, point number 3 H3, 4 you can use this upper side scale because it is nearer, 4.5 here enthalpy this. Now enthalpy of 5 and 6 same. Later on point number 7 you can take this enthalpy, 7 and 8 you will find this enthalpy. So in this way all these enthalpies we can get from the chart. These enthalpies we can enlist in the numerical process. So here now the pH diagram is again drawn for the better understanding. Here all these values what we got from the chart, these are enlisted, all the enthalpies. These enthalpies now we will use to solve the problem, that is a work done in the next slide. Before that we have to find the mass flow rate. So mass flow rate formula m1 dot, that is in the form of cooling capacity. Cooling capacity is given to us, m1 dot is equal to cooling capacity divided by enthalpy difference across the evaporator. So at the evaporator process is what, between point number 8 and 1. So that is why here enthalpy difference comes H1 minus H8. Q dot N. Now as in the numerical value is given in TR, conversion TR to kilowatt, this multiplier we use. Putting enthalpies over here and doing this calculation, we find the answer, that is mass flow rate passing through the low pressure compressor C1. To find the mass flow rate of high pressure compressor M2 dot, as already we have seen this explanation in a theoretical video, that is earlier video, that is a complete multistage system. Their energy balance equation at the flash tank, we have seen that 4 lines, 2 lines going in and 2 lines coming out from the flash chamber. So here you will find here summation of these 2 lines entering, summation of these 2 lines coming out of the flash tank. So here as per the formula, m1 dot h2 plus m2 dot s6 is equal to m2 dot s3 plus m1 dot s7. Now first of all we will arrange this formula for the better calculation or easy calculation. We take the terms of mass flow rate m1 dot one side and this m2 dot mass flow rate terms other side, and here in the bracket now corresponding enthalpies what we enlisted in the last slide, H2 S7 we put here, m1 dot calculated value we put here, m2 dot is unknown, H3 S6 enthalpies from the previous data we put here. Here by doing this calculation, we find the answer, that is mass flow rate of high pressure compressor 2, M2 dot. After that, here, if you see work done calculation for the compressor 1 and 2, work done W1 dot for compressor 1 is equal to what? Mass flow rate 1 multiplied by H2 minus H1, enthalpy difference across compressor 1, M1 dot value, H2 minus H1, these are enthalpies from the data. If you do the calculation, you find the value in kilowatt. Similarly, for the compressor 2, mass flow rate 2 value, 3 and 4 is a process, so across this H4 minus H3 will be enthalpy difference. By putting the value of enthalpies and doing the calculation, you get the consumption of high pressure compressor. Total consumption means power, total power to run the system will be what? Summation of W1 dot value and W2 dot value. So this in a kilowatt we find. And then we find the coefficient of performance is what? Q dot L divided by total power. Q dot L is in TR, conversion into kilowatt by using this multiplier, divided by this total power. So by doing the calculation, we find the COP. Now in this numerical, here we have seen that how to find, first of all, mass flow rates, then mass flow rate of low pressure compressor, high pressure compressor, then consumptions, power, then COP. Now in some numerical, you may be asked to find the volume flow rate. So to find that, we need to use the formula, and we need to first of all to find the value of volume, specific volumes. So 1 to 2 is a compression 1. So entry of the compressor 1 is 1. So specific volume of 0.1 V1 dot, V1, not dot, V1, because it is a specific volume. Its unit is meter per kg, meter cube per kg. So V1 here we find from the chart this value. Similarly, for second compressor, 3, 4 is a process. Entry of the second compressor is 0.3. So through this 0.3, we have to draw a line, specific volume line. Now specific volume lines will be, I will show, because this is the first time where we have to see. In earlier, this kind of explanation was not come. So let us see in the chart where the specific volume lines. Here you can see point number 1. So on the chart, if you see these dotted lines, these are constant volume line. Here is a written constant volume meter cube per kg, and their values are given here, 0.2, like this. In this way, in upper side, these values are given here. So here we are concerned with point number 1 here. So through this point number 1, you have to draw a line between the reference lines of these specific volume which are available. So here are 2 dotted lines available. So near to this dotted line, you can draw the line, and then you can get the value of this point by doing the interpolation of these 2 values, because lower dotted line this value, upper dotted line this value. These 2 value, between that your actual is V1 dot V1 will come. Same method you can use for the second compressor. So second compressor, let us first of all see. Yes, here point number 3. So same method we use. Here is a point number 3. Through this point, you have to draw a line with reference to these 2 dotted lines, which are on the both side of point 3. This one upper finger, this forefinger, index finger, and this is a thumb. So here is a thumb and this is the index finger. So this is a dotted line and this one dotted line. With reference these 2 dotted lines, you have to draw a line passing through this point number 3. And then you have to take here reference of these values, this value and this value. So by doing this calculation, you can find the specific volume of the point. So here, by doing that process or workout on the chart, we obtain V1 specific volume of compressor 1 and specific volume of compressor 2. Now these two specific volumes will be used to find the piston displacement. Piston displacement will be what? Volume flow rate actually. This is V1 dot will be equal to corresponding mass flow rate into mass specific volume. So mass flow rate M1 dot, we use the value V1 dot, just V1 specific volume. We have just seen that here. By doing this calculation, we find this in meter cube per second. Similarly, V3 dot will be equal to, because this is volume flow rate, V3 dot is equal to M2 dot, means mass flow rate of second compressor into specific volume of second compressor, V3. So here are two values we have put. Doing the calculation, we find the mass flow rate here. So in this way, these are the what piston displacement of compressors. So in some numericals, sometimes it is said that mention the piston displacement in a meter cube per minute. So you can do that calculation and you can mention in meter cube per minute also. For that, you have to multiply the value of meter cube per second by 60 to convert that into meter cube per minute. So by that also you can get the answer in meter cube per minute. So as per the requirement, you do the calculation in the numerical. So in this way, we have seen the descriptive explanation for the solving numerical on the complete two-stage compression system. That is a third type of multi-pressure system. In that, we have seen complete idea how to locate the points on a pH diagram by using the data of the statement, that is a evaporator temperature, condenser temperature, and intermediate pressure or temperature of flash tank. After that, drawing the vertical horizontal lines, isentropic lines, then complete cycle, that is both envelope, low pressure, high pressure envelope. After that, following all that points on the pH diagram scale, getting the enthalpies, and then all these values we put in the formula and getting the answer of mass flow rate of the both cylinders, then power consumption of both compressors, total power to run the system, COP of the system, and piston displacement of the compressor when it is asked in the numerical. So let us meet in the next video session of the HVAC R.